In this video I'm just going to explain one of the really handy uses of defining the scalar product in the way that we do, and that is to calculate the angle between two vectors even when they're given to us in component form. So this saves us having to sort of calculate them into polar form and then working out the angle between them. But even more so when our vectors are in 3 dimensions, as we'll see in Unit 3, this is incredibly useful. So let's remember our definition for the dot product. We said the geometric definition is that the dot product of A and B is equal to magnitude of A times magnitude of B times the cosine of theta. So if we just do a little bit of rearranging on that, then we can say the cosine of the angle between them is equal to their dot product divided by the product of their magnitudes. Now that's not a formula that is given to you on the formula sheet. You do have the one above it, the geometric one, and also the component one. We're not given this one on the formula sheet, but as you can see there's no real need to learn that one because it follows on pretty simply from the geometric definition that is given to us. So let's think about how we could use that to find the angle between two vectors. Let's use, I think these were the vectors that I used in the last video. So we had A was 3i plus 5j and B negative I plus 9j. Now you don't need to sketch these, you might like to sort of visualize them. So what have we got? 3i plus 5j would be, I guess, something like, roughly like that, and negative I plus 9j would be maybe something like that. Now that's pretty rough sort of sketch there, but so we'd be trying to find this angle between them here. Okay, well, using our definition, or the rearranged definition here, we're saying that the cosine of the angle between them is equal to the dot product of these two. So the dot product of 3, 5, negative 1, 9, and then the divided by the product of their magnitudes. Don't have too much room here, but let's say 3 squared plus 5 squared, and then the square root of 1 squared plus 9 squared is going to be the magnitude of the second one. So that's just using that definition or rearranged expression in the red box above. So let's do some calculating here. So in the previous video I actually found the dot product of A and B. It was negative 3 plus 45, which is 42. And what are these two magnitudes here? So we get 9 and 25, which is 34. And the second one is 1 plus 81, so that's going to be root 82. Now then you can grab your calculator out and say, well, therefore theta is going to be the inverse cosine. Oh, little glitch there again. So we're saying the inverse cosine of that expression there, and you can just sort of whack that straight in your calculator there to get an approximate value for that. And here's one I prepared earlier, 37.3 degrees. Now from our sketch up there, I guess that kind of looks reasonable. Our sketch wasn't totally accurate, but certainly around 35-40 degrees looks reasonable for that. This also lends itself to one of the other really useful things about angle between vectors and the result of the dot product, and that is that if two vectors are perpendicular, so if A is perpendicular to B, in other words the angle between them is 90 degrees, well, because the cosine of 90 is equal to 0, that means that the dot product is going to be equal to 0. The dot product is going to be equal to 0. And it's true the other way as well, that if the dot product is equal to 0, then two vectors are perpendicular. Now again, that's not a result that is on your formula sheet, but that's one of the really handy ways that we're going to use the dot product in a number of different applications. That is a way of showing that two vectors are perpendicular, is to show that their dot product is equal to 0, or to say, are two vectors perpendicular, and check if their dot product is equal to 0. Alright, so that's a video showing angle between two vectors and also the important relationship between perpendicularity and dot product.